So yeah, I'm Santiago Manent, and this is joint work with Dr. Radu Timofte, Deng Xindai, and Professor Luc van Gogh at ETH Zurich. So in this paper, we address the problem of multi-target tracking, that, as other presenters have said before, what you want to do in multi-target tracking is to compute the trajectories of objects of a known class, and you want to find all the objects of this known class in a video. So how you do it is that you start with object detections. You start with object detection at every frame, and then you want to associate them according to certain affinity measures in order to obtain the full trajectories. So this is usually done with a global optimization in which you have three types of energy functions. So the first energy function is the detection confidence cost. This detection confidence cost basically encourages using good detections to associate them into trajectories and penalizing bad detections that are probably false positives. Then you have some entry and exit costs that are usually considered constant, and they basically are an indirect way of controlling the number of trajectories. And then you have the affinity measure. So the affinity measure is actually the one that tells you what is the probability, the likelihood of two detections belonging to the same object, just in different frames. So in this work, we focus on this affinity measure, and we propose the trajectory overlap affinity. So this trajectory overlap affinity is based on single tracking trajectories. So single target tracking compared to multi-target tracking is a different task in which you are interested in one object of an unknown class and you have a first bounding box initialization. Then you can track forward or backward in times. One of the properties of the single target tracking is that it's very accurate at the close to the initialization, and then afterwards it can start drifting. But we use this property for our affinity. So let's say that you have two detections and they can be temporally distant. So what we propose is tracking forward and backwards from each detection towards the other one. And then we can do this in parallel or sequentially for each detection. And then for each pair of detections, what we measure is simply the overlap. We extract some features from the overlap and the distance between these two trajectories. So basically, we learn a logistic regressor. And this logistic regressor learns that if these two trajectories have a high overlap, then it means that they are most likely coming from the same object. So we run experiments on the MOD benchmark, and with the standard network flow formulation and this very simple trajectory overlap affinity measure, we obtain state-of-the-art results. So yeah, I mean, our affinity allows for high recall while keeping a very high precision. So thank you for your attention.